All right, everyone. Welcome to ASRG Live Worldwide Webinars, bringing you the latest in automotive security research, innovation, and education. My name is John Heldreth. I'm the founder of Automotive Security Research Group. Today is February 18th, and we're streaming to you live from Stuttgart, Germany. So, first of all, before we jump into everything, I'd like to quickly introduce myself. As I said, my name is John Heldreth. I'm the founder of Automotive Security Research Group, or ASRG. I've been working in the automotive industry for the last 15 years or so, and now I focus my time on product or vehicle security. I'm originally from Detroit, Michigan, in the US of A, but today I'm living in Germany and working at Porsche Engineering. Today, I also have with me Sven Schran. Sven, would you like to quickly introduce yourself?
In my professional life, I work for Robot GmbH as product security officer.
Great, Sven. Thank you so much. I think we only heard about half of it, but Sven Schran, he's working at Robert Bosch as the product security officer here in Stuttgart, Germany as well. Sven, thanks for being with us tonight. So let's get things started here. I just want to give a quick overview of what the Automotive Security Research Group is trying to accomplish. We are a nonprofit organization focusing on the advancement of the automotive security industry. This is a community to support the coming together of two areas of competencies: the IT security market and the automotive market. This is a community for you, for the automotive engineer, for the IT security specialist, for the beginner, the hobbyist, even for the people that have no idea what security really means. This is a community of volunteers. Our entire organization is built on the volunteer efforts of the administrative team and, of course, people like yourself. We're trying to remove the boundaries that can occur in the automotive security industry. This could be something like communication, borders, finding different ways to learn or new solutions, making good decisions, because at the end of the day, we all have the same goals: to keep our customers, our families, our friends' data safe and secure, which can only be done together. If you want to get more involved, make an impact on the industry, start your own ASRG location, participate in a technical committee, or be a part of a project, please reach out to us. You can find out more information at ASRG or at www.asrg.io, or send us an email at hello@asrg.io. Remember, this is a community for you, for us. Be a part of it. So, just quickly to give an update, we have this survey going on right now. And this is really important for us. We're working together with Cybellum, and Cybellum is a new sponsor of ASRG. And they're actually going to bring vulnerability management to all the ASRG members. That's right. We are going to have a portal, a platform where we can look up which vulnerabilities are attached to which projects, solutions, what's going on. Because the more we know about what issues there are in the field today, the better we can prepare our products for tomorrow. So we are right now in the requirements management phase, and we need to know what you need for this new vulnerability management system. And it's really important if you guys can take the time, take the 5, 10 minutes or whatever it is to take this survey so we can make sure that the new vulnerability management system for ASRG members is what is needed in the industry. So here's the QR code. The link is in the description notes. please take the time and do it because we really need this to make sure it's what you guys need. All right. So moving on here. Where am I? So ASRG around the world. We're now 6,300 members, actually more than that. Every day we see so many new members joining, and it makes us very happy and proud. Um, but you have to remember it's not about the numbers, it's about the community, okay? So um, here I have a map of all the different places where we have an ASRG location. So please take a look, find a location that's near you, because one of the things about ASRG is to network, to come together, to talk about things. What issues do we have in our area? And so it's really important that we have local locations where we can discuss such topics. If you don't see an opportunity or if you don't see a location near you, there's always the opportunity that we can create a new location. So please reach out to us at hello@asrg.io if you see an opportunity for a new ASRG location near you. Guys, we have some really cool webinars coming up. All right. This is an amazing initiative that kind of was brought on by COVID, but to do webinars and make them virtual so that everybody can join from around the world. So next week, we have Thomas Liefert from Keysight Technologies. He's going to be talking to us about testing. We don't have a title quite yet, but it's going to be about how to test security. Then on February 25th, we have Intro into In-Vehicle Networks and CAN Hands-On. If you don't know this guy, Camille Gali, he is like the I don't even know what to say here. The penetration test ninja. He's working for White Motion, and he's going to give kind of a hands-on workshop about how to reverse engineer. How does the in-vehicle networks work in a vehicle? So check it out. It's actually going to be on Japan and Asia time, so it might be a little early in the morning for us on the EU side of the world, but check back. The video will be on YouTube. All right. Then the same day, just in a different time zone, we're going to have Redefining Cybersecurity for the Third Screen, From Safety to Privacy, with Andrea Amirko from Privacy for Cars. Going to be an interesting talk here about how privacy is affecting us. March 4th, Attacking SoCs by Side Channel or Laser Fault Injection, a Grail's quest. So Hugh Thibault is going to be sharing this presentation from eShard. Great stuff there. Laser fault injection. Interesting. March 11th, 2021, an AutoSAR-based solution for automotive IDS. We're going to have Vector back in the house with us. Dr. Metzger is going to be presenting here. Going to be an interesting topic about intrusion detection systems. If you would like to present at ASRG, please, we love to have presentations from the community. Please get in touch with us, cfp@asrg.io. All right. So without further ado, and without me talking further tonight, I'd like to introduce to you guys Cristofaro and Niek from Raelize. They're going to be talking today to us about voiding trust in real-world trusted execution environment attacks, TEE. So, Niek, I think you are up first, sir. Is that correct?
Thank you very much, John. That's correct. Welcome, everybody. I'm very happy to be here together with Cristofaro in order to give you an insight in some of the research and topics that we've been analyzing the last year. This presentation is a composition of a few different things, including training that we actually provide commercially as well. So I think it is very hands-on. There will be demos during the presentation as well. We will take our time. We will not rush things. But let's start with the overview of the talk. So we'll start off with an introduction about ourselves, but also some of the topics that we'll touch upon. We will take a brief moment into touching upon the usage of TE in the automotive industry. We will explore the TE attack surface. We will discuss various attacks towards TEs, and this includes the demonstrations that I mentioned earlier. We will also discuss briefly mitigations and recommendations from when you're using TEs and how to do this securely. And at the end of the presentation, there will be a moment for a Q&A. Let's see if that will work out. We may ask ourselves a few questions and answer them, or maybe John or Sven would like to pitch a question to us that we answer. Let's see how that goes. So last year we founded a new company because I was already working together with Cristofaro on a research level a lot. And at some point we decided to join forces professionally in order to provide various industries with our expertise. So during the last decade and more, we actually analyzed the security of devices. And what we really like is the area where the software actually meets the hardware. So we really like the technologies related to device security where both the hardware and the software are fundamental and relevant. So this typically means that we like to look at low-level software and hardware things like operating system, trusted execution environment, secure boot, fault injection, and all sorts of things that come on our path. So more simply said, it's not like we never do it, but typically our interests are not triggered by, for example, a Windows application or just a Linux application that's running on a laptop, for example. We really like to get our hands dirty into looking to the security of devices. So we started a company where we provide consultancy and testing services in the space of device security. So for example, we work for manufacturers, security labs, and other entities that play a role in the device security world. So like I said, we provide training. So at the moment we offer two trainings. One is on secure boot, which is called Bootpan. And we also have a training on trusted execution environments, and that will be actually the topic for this talk. And also we like to dedicate a significant amount of time to research, and we like to blog about this on our website. So the topics that we'll touch upon is always related to device security, but you can expect things that are related to low-level software and attacks like fault injection. So why do we have this talk? Well, we noticed that multiple industries actually adopted the TE technology that was roughly introduced about 10 years ago successfully. So TEs are very prevalent in markets about mobile, payment, pay TV, in order to make sure that you can watch DRM protected content on your TV, for example, there's typically a TE involved. In a similar way, if you want to do a payment with your mobile phone, that typically means that there's some form of TE involved in order to do this securely. Now, we also noticed that this technology is also being adopted in new industries, and new industries meaning new industries for TE technology. So one example is the automotive industry. So that's one of the reasons why we're here. So we think we can add something to the game board regarding TEs, also when they're used in the automotive space, because we think it's very important that we can learn from the past and that we can reduce the risk of mistakes. Because some of the hurdles the automotive industry will have when TEs are being used and being implemented, they will be similar to what we've seen in the mobile payment and pay TV space, let's say about 5 years ago. So what we're trying to achieve with this talk is that we spread awareness about TE security, and also that we share some of the knowledge that we acquired during those last 10 years. Of course, we cannot put everything in one single presentation, but this presentation has its purpose to give you an insight into the things we think about when we talk about TEs. So let's start by having a cup of tea. So there's many different type of trusted execution environments you see. We will not dive into all the nitty-gritty details during this presentation, but it's important to realize that there's a few things that all these TEs have in common. So typically what you see is that there's some form of hardware platform, or you could say a chip, that provides the handles or the functionality that allows you to have multiple environments. So in a simple fashion said, there's a non-trusted or a rich execution environment. So quite often this could, for example, be a Linux operating system with its applications. And there's an environment that is considered trusted. Typically there you find a much simpler operating system. And also there's various use cases implemented by means of applications. So this is very generic, but it's important to realize that a TE is about software and hardware. You cannot implement a TE with only software, for example. There's always some form of support required by the hardware. So why do industries need a TE? Well, many industries started realizing is that there's a need for separating safety or security critical use cases. And a typical chip, which you now find in a modern device, actually provides a lot of different type of resources, whether these resources are external or are within the chip itself and by the means of hardware modules. There was a need to actually provide adequate partitioning on those resources. That is not possible if you have only software running in one particular exception level, for example, a privilege level. So you need some hardware in order to guarantee that. So having that just in software is not enough. And also, once you implement these things, so this partitioning in hardware, then it should be more resilient to certain type of attacks. But at the same time, you cannot do everything in hardware because then the development of a given system becomes very complicated. Because once you embed something in hardware, you may have some means of reconfiguring this, but typically it's fixed. So it's not so flexible. So there's also a large need to have a lot of the functionality that you want to implement, whether it's in the secure world or a non-secure world, to have this done in software. And this is exactly what typical TEs provide. So this is a so-called golden mix of hardware and software that is able to meet the safety and security levels that are required for a particular industry, but still flexible enough that is not too costly to develop on these products. For example, you don't want to create a new use case for every, or you don't want to create a new chip for every use case. So you want to be able to reuse chips for multiple use cases. So definition. Well, a TE is often believed to be a processor feature, and that is slowly changing. But for example, if you still would go to Wikipedia, you will notice that there the definition is not entirely correct. So a trusted execution environment is not just a secure area of a main processor. And we will see today why this is not entirely correct. So our definition for a TE, to start off with, is an execution environment for security critical use cases, which is separated from a less trusted RE. So that was the green block on the left side in the previous picture. But this separation from the less trusted RE is done by leveraging a strong cooperation between hardware and software. So it is the golden mix of software and hardware that the TE provides in order to be resilient, but flexible and convenient for development. So what are TEs used for? Well, let's touch upon some of the automotive use cases that are already implemented or that will be implemented in the future. You can think of virtual keys, including sharing of these virtual keys in order to open your vehicle. Digital rights management, so very similar to the example I gave for the TV, where it's possible to decode or descramble the content for which you need to pay for, or for which you need to have a valid license. You can think of vehicle sharing, secure over-the-air updates, payments that can be done from the car. And there's a whole variety of different use cases. And probably you're well aware of the use cases in the automotive space where TE might become relevant. So let's have a look at some of the automotive-related adoptions that we already noticed in the automotive industry. So one nice example is the Apertis platform. It's a Debian-derived GNU Linux distribution which can be used for developing an ECU, and it's basically tailored towards infotainment and telematics. And it's much more than just a distribution. It also provides all sorts of APIs, tools, and services that can be used in order to make it less complex to make an entire connected ECU. So one of the nice things about the Apertus platform is that it's security driven. So one of the suggestions they make is to use TE technology in order to implement hardware-based security, which we think is a good idea. So for example, one of the use cases they describe is for authentication. So the idea there is that a secure environment is being used, in this case a TE, to protect the secrets that are used by the vehicle, or by this case, these ECU. So what you can see, what's happening is that there's an application that's running within the car. It wants to connect to the cloud service. So it's a connected car. So the request is being made, the cloud service sends a challenge back. And then this secure environment is used to sign this challenge so that the cloud service knows that the car has not been tampered with, so that the secure environment is present. So this prevents a car from authenticating to the cloud service without having the secure environment in place. So it's impossible to store the keys that are used for this authentication without hardware, because if it's just implemented in software, then within no time an attacker can take this out. So traditionally, this was done using an HSM. And this HSM can be an HSM on the chip itself, or even an HSM that's external to the chip, so still on the PCB of the ECU. But having an additional chip is quite expensive. So the same functionality, the same protection can also be implemented using a TE, which is actually integrated into the chip itself. So you could call this a VHM, so a virtual HSM, for example, but we like to refer to it as simply the TE that can provide secure storage. And of course, when this is a feature that's provided by the chip itself and it's always there, then it's likely to be way less expensive than having an additional chip to store those keys securely. Another example is the VOSIS monitor, which actually uses ARM Trust Zone to co-execute both a safety-critical RTOS and general purpose operating system. So effectively, what they do is they use the secure world in order to perform safety-critical operations. So it's an interesting approach. It's maybe not something that ARM initially intended for their ARM Trust Zone, because it's mostly focused on the security aspects. But of course, as we know, security and safety definitely have overlapping requirements. Even though they're not exactly the same, that means that some security features definitely can be beneficial for safety-critical operations as well. So we think that all modern vehicles that will be produced will include at some point a TE. There's a wide variety of use cases that are applicable, and time will tell which use cases will exactly be implemented. We would, if you have any ideas about this, feel free to reach out, because it's always interesting to hear about these use cases. But we believe there's many, and that's one of the reasons why we'll see these technologies being used in the cars of tomorrow. So let's take a brief moment to look at the TE security model. Well, we looked already at this picture, so we know that there's a hardware platform able to provide the separation between the rich execution environment and the trusted execution environment. So that is the fundamental separation that needs to be implemented. However, there are also the use cases that are implemented in the trusted execution environment. And it's important that those use cases, which are implemented often by means of a trusted application, are implemented securely and also separate from each other. You don't want your payment application to have access to the DRM keys, for example. So these TAs need to be separated adequately. And when you want to separate the applications, and effectively what we mean with that the assets of trusted application 1 cannot be accessed by trusted application 2, then it also means that the trusted application needs to be adequately separated from the TEOS, because if the trusted application can simply break into the TEOS, then nothing prevents the trusted application from breaking into another TA. So typically when we talk about the separations of a trusted execution environment, we talk about these three separations. So it's also important to realize that the TE is as strong as its weakest separation. So that also means that if you break one of those separations, then the security provided by the TE cannot guarantee it anymore, and the TE will likely be fully compromised. Now, we've talked at a high level about separation, but what are we exactly separating? Well, we talk about four main dimensions when we talk about those three separations. The first thing we need to separate, or the TE needs to separate, is the execution. Simply said, you don't want the code that's executed in the untrusted side, the rich execution environment, to simply execute code that is executed in the trusted OS. So you want to make sure that whenever code is executed at a non-trusted privilege, it cannot interfere with code that's being executed in a privileged context. The same thing holds up for the memory. You don't want to have the RE, so the untrusted side, to access the memory that's used by the trusted side. So if you don't have a separation in place to make this distinction between those two types of memory, then there's nothing you can do to prevent an attacker that's already in control of the RE to access things that are stored by the TE. And of course, this includes very likely secrets that the use case that's implemented in the trusted side relies on. It's also important to realize, and we already touched upon this briefly, that there's much more within the chip than just a processor. So there's much more than the execution that needs to be separated. There's hardware modules in there as well that can be used by both the untrusted and trusted sides. So there needs to be adequate separation there, that the trusted hardware module cannot be used by the untrusted side. And in a very similar fashion, this also holds up for the input and output, so the peripherals. For example, if you have a fingerprint scanner or a biometrics authentication device, you don't want the untrusted code to interfere with that operation, because otherwise the untrusted side could, for example, get access to the fingerprints that are used to authenticate the user. So these are the four separations, and let's see what parts of the system actually implement those separations from a software point of view and what sits there, because it's quite complex to put all the different pieces in place. So this is a slightly more complex picture than what we looked at before. So this is our so-called TE reference model. At the bottom, again, you see the hardware platform, which is now a little bit more detailed, where you see that it needs to provide the primitives for allowing the separation to happen. So the execution separation, the memory separation, the I/O peripheral separation, and the hardware IP separation. And also it's important to realize that lots of the stuff for a TE, lots of the functionality is implemented by software. And it's important that this software is initialized securely. So the hardware platform also needs to provide a root of trust. And typically this is referred to as secure boot, which can be used to guarantee that everything that's executed, including the bootloaders and including the TOS and including its trusted applications, are actually authentic, so that nobody tampered with it. So once this system is fully initialized, we see that at a given privilege level, you see the OS and the OSS drivers. There may be an application running at the same privilege level, but that depends on the architecture of the T software itself. And you see that all the applications that implement a specific use case are executed in their own little zone. There's not only use cases implemented as trust applications, there can also be services that are provided to the other applications that are implemented at user space level, or there may even be drivers implemented at user space level. So this is just a generic picture what you can think of from a hardware and software point of view when you start thinking about the TOS. And again, this is still agnostic of any specific technology whatsoever. These are just the typical things that you'll find in a given TE. And these are basically the minimal things that you need in order to make sure that you can implement a secure TE. So let's look at the first threat. So I already touched upon this. An attacker may be able to be in control of the RE. So once an attacker is in control of the RE, the attacker can decide to do a few things. It can start attacking trusted applications. It can start attacking the TOS. It can start attacking the bootloaders that are used for initializing the TE securely. And it can start attacking the hardware platform. Some examples of these attacks we will touch upon later in this presentation. Another threat is that an attacker is actually in control of a TA. So once a TA is compromised, for example, from the RE, an attacker is able to compromise the TA, but the TA that is compromised does not have the secrets that the attacker is after. For example, the DRM TA is compromised, but the attacker is interested in the TA that's handling the virtual keys. Well, then the attacker can simply attack the TA from another TA. Similar fashion, from one TA, the TOS can be attacked. And once the TOS is compromised, the other TA can be attacked again. And also from a given TA, the hardware platform can be attacked. So these are typically the two types of attackers we think of when we think about the attack surface of a TE from a software point of view. So let's dive a little bit into a specific architecture, a specific technology that's often used to implement TEs. And this is very common. And it's very likely that there's cars out there nowadays that implement this technology for various use cases. So ARM Trust Zone, and specifically is ARM v8. ARM v7 works a little bit different, but the key ideas are still the same. So very similar to as a generic example, there's two worlds, untrusted and trusted. This distinction extends much further than just the processor. So it also affects the buses, the memory, the peripherals. So this is in line with our reference model where we saw that the hardware platform needs to provide also the separations beyond just the execution. And the execution of the trusted side is upon request. So this means that the TE does actually not execute in the background. The RE is responsible for issuing requests towards the TE, and then the TE starts doing things. So modern ECUs, and I'm quite sure that some of you will be aware of this, are actually using ARM Trust Zone, and they do this in a fairly complex manner. During this talk, we will not touch upon all these things that are in this picture. So we will not be talking too much about the hardware side, so the physical HSM, which might be still used for a given ECU. And also we will not be talking too much about the virtualization, which is becoming very relevant in the automotive industry especially. This is maybe something we can do in the future, but for this presentation, we will mostly focus on the TE side itself. So we talk about the RE as a whole, and the TOS and its applications as the secure world, and there's the secure monitor, which allows you to switch between the worlds. So this is the simplified view that we'll be talking about today mostly. So what separates those worlds? Well, it's hardware, right? That's the whole point, that we want to use a TE. Well, it's true, but the separation is implemented actually using a single bit. So there's a special register, which is called the Secure Configuration Register, which is an EL3 register. And basically within this register, there's a single bit that determines if a particular operation is done in non-secure or secure mode. So whenever this bit is set to 0, all the requests from the processor will be done in will be considered secure. And if this bit is set to 1, then the request is considered to be non-secure. Now, whenever you hear people talking about ARM Trust Zone provides hardware security, actually what these people mostly are talking about is just this single bit. That's quite interesting, considering that typically when you think of hardware security, that there's much more going on. But this bit implements the boundary between secure and non-secure. That's something to keep in mind. Well, I mentioned it already a few times. There's much more than just a single processor in a chip. And there's actually multiple processors typically inside a chip. So there's, for example, the ARM, the application CPU, that's what we've been talking about mostly. That will be running the TOS and the TAs. But there's also, for example, a Wi-Fi chip or another communications chip like a modem. All these systems are executing software. And all these IP or all these modules are sitting on the same bus as the application CPU. So that means that these processors can issue the same type of transactions as the application CPU would. Same holds up for other masters on the bus. It's not only processors that can issue transactions on the bus in order, for example, to access memory or to access a particular module. There's also, and this is just one example, there's masters on there that allow you to copy memory efficiently, so-called DMA engines. So these are able to copy memory from A to B without any interference of software. You just need to configure it, or you need to provide it its configuration. You hit the start bit, and it will copy the memory from A to B. So it's important that there's a distinction being made between those modules, because if this is not done, then the problem can be is that if you compromise the modem, you may be able to access secrets that are adequately protected by the TOS. So that's why for an ARM trust-based system, you need to implement a few controllers as a chip manufacturer that allow you to make this distinction. And actually what's typically done is that the NS bit that is also used to indicate if a code is executed as trusted or non-trusted, as secure as non-secure, that the same thing can be done for the transactions that are being made on the bus. So this allows the chip to distinguish the transactions between non-secure and secure. And this allows you to, for example, dedicate the fingerprint sensor only to the secure world. And that means that the non-secure modules and the non-secure software that's executed cannot make use of the fingerprint sensor. So one piece in this simplified model is very important, and that's the secure monitor, because that's responsible for switching between both worlds. And also it's important to realize that this actually executes at the highest level of privilege within the system. Even when the hypervisors are implemented in the more complex picture as shown before, EL3 is still the highest privilege. So if you compromise EL3, there's nothing you cannot do in the system, typically. And it's also important to note, and I think I said it already, but I will stress it again, the EL3 code is responsible for modifying the NS bit. It's not hardware taking the decision to change the NS bit. It's software changing the bit in that register, and the EL3 software is doing that. So if you compromise the EL3 runtime software, you can arbitrarily send or set this bit to 0 or 1 in order to make non-secure or secure requests. So it's very powerful, and therefore this secure monitor should be handled with great care. So the switching is actually done by trapping the secure monitor using an SMC instruction. So this SMC instruction can be executed in the RE, for example, by the kernel or the hypervisor. And once it does, it basically passes control to the secure monitor by means of an exception. And once this is done, some of the registers that are set up by the RE are used as arguments for the secure monitor. So typically you provide values there or pointers, and whenever there are pointers, then it means that these pointers must point to physical addresses. And the reason for this is because the secure monitor and the TE as a whole is not aware of the RE's virtual mapping. So typically an RE needs to translate the virtual mapping that is using first in order to provide the physical address to the secure monitor. And then, of course, the secure monitor, or when the request is forwarded to the TOS, must take great care in sanitizing those values and pointers that are being sent from the untrusted side. And now we're going to dive into the attacks, because we're going to see why it's so important to sanitize those values and pointers when they are received from the untrusted side. So at this point, I would like to give Cristofaro the stage. So I will stop presenting my screen so that he can take over. And I will mute my microphone. Thank you.
Yeah, thank you, Niek. I'm just switching to my screen at the moment. And slides should be visible, right? Can you confirm?
Yeah, they are.
That's great. Well, now let's see why basically the pointers needs to be sanitized by the TE. And we start immediately with an example. So what you're seeing in this picture is an SMC handler. So it's code which is running on the T side, actually in the monitor. And this monitor takes the ID of the SMC call that needs to be, let's say, processed. And it uses the registers as parameters, exactly what Niek was saying. So this is actually code that is very likely present in modern devices because it's taken from ARM, from the ATF, trusted firmware, basically. Untrusted firmware, and so we are just using this as an example. So you see that the registers here are passed from the RE. So when it's disturbed, what you have here are the value which have been preloaded by the RE in the registers. So basically, this interface is triggered by the RE. So what's wrong in here? What do you see? What could be going wrong? Well, I know that you cannot answer me, but if you think for a few seconds there, you should probably see that there is a vulnerability here. And the vulnerability is actually in there, because what's happening? There is a version, which is the version of the RE, or the TE, sorry, which is stored at the location provided in X1. But this means that if you provide a physical address, which is part of the TE memory, you are effectively overriding TE memory with a version number, or with a combination of bytes that is returned by the function. So you are assigning that location from the version number. Well, it may be that you don't have that much control because you may not be able to change the version, but you can say where this value needs to be stored. And because it's a physical address, it can be basically anywhere at this point. It's a physical address provided by the RE. Then the problem is that this vulnerability will allow you to write to arbitrary TE memory. And we know from an exploitation point of view that as soon as you have write capability to a memory, with a certain degree of control, which could be also almost none, then it's possible that you may turn a write primitive or an arbitrary write primitive into an execution primitive, basically. So basically, you think that, yeah, this is a naive, let's say, bug and a naive implementation, because in principle you should not be able to pass pointers to the TE memory. But actually, we have seen even much worse than that. Let us refer to research, which is probably one of the first research, public research in TE security, black box binary done by a Apertis partner in 2014. And basically, by analyzing the HTC mobile phone, they have seen that among the SMC handlers that were available, so the MC capabilities that were there were some interesting primitives, like being able to read memory. So it's not because of a vulnerability, but because of a feature that was added to the SMC handlers. You would be able to update secure memory, to write to memory anywhere, and even be able to do a memcpy. So you basically, instead of calling in the previous slide just a function that has a version, you could actually call the equivalent of a memcpy, which would allow you to copy between secure and non-secure world, because this code is running in EL3. So this means that, or the equivalent of EL3 at the time. So the IO is privileged, and it can access secure memory. It can access non-secure memory. There is nothing preventing an attacker from being able to read secure memory by copying out to RE, or by writing to the T, by simply copying from RE to T. So if you're ever in a situation of reaching in an exploitation, or the ability to copying out TE memory and writing in TE memory, well, you are basically done. And well, let's do just a little bit of light demo. And so let me switch to our T-Pound platform in order to do so. Just 1 second. Yeah, okay. It should be visible now. And what you are seeing now is that this is a platform that we use for demos, for training, and things. So what we are going to do now is that we are going to start a real TE, a system with a TE and RE. You see it's booting, and what you're seeing on this side is the printout of the TE. What you're seeing on this side are the printout of the RE. And this is our, let's say, debugger, more or less. It's where we are able to perform a number of operations on the entire device, because that's basically an implementation of a device. And here we have our console for doing a number of things. So without further ado, we just log in. We log in the RE side, and we can log in as root. In principle, the root account should not be able to compromise the TE and so on, and all these things. So what's on the other side? On the other side, we have basically implemented the same vulnerability that has been found by a 3D partner. And you're seeing Hydra here. And this is basically the SMC handler. And one of the SMC handler that we have implemented actually calls a memcopy. So it takes parameters from register X1, X2, and X3. The SMC ID is X0. And it just does a memcopy operation. This is actually the simplest and, let's say, most powerful primitive. But in order to make it visible what can be done, and we are just going to replicate live the attack that was possible at the time. So there is nothing to do basically here other than just taking your code from RE. This is the source. So this is the destination, and this is the size. So if this X2 points to RE, where you have your payload, your shellcode, and X1 points to TE memory, you will be able to write to TE memory. So it should be not surprising here that if this becomes an RE pointer, let's label stuff because it's always useful. Pardon, this is X2. Yep, okay. So basically, if you put a pointer from RE memory to an X1 to a pointer to TE memory, you will be able to write into the TE. So what can be written here? In order to replicate the real attack here, there were another additional things. We actually had to disable the MMU. Why? Because in the real target, there was the MMU was actually not enabled. So this means that there was no read and write and execute permission applied to the memory pages. They were basically not there. And don't be surprised if this. Nowadays, actually, most of the TEs do have a proper implementation, but don't be surprised because you might encounter devices where the MMU is not even used at all. And so what we're seeing is that an attack from 2014 could still be possible, as we are showing in some class of devices, which are a bit behind in security. So basically, we have these running on the other side. This is our TE side and the RE side. And we also have, let's say, a shared directory that allow us to do a number of interesting things. So we have already created the code for our exploit, and we are going to comment that. So what are we going to do here now? Yeah, let me set order up. So what we're going to do is that we have a payload that we would like to write. So this is the payload to call a function, which actually is a notice function. This is x1. It's the address of notice is loading in x1. And what is this notice function? You see that there is a notice here. It can just print stuff on the screen. And indeed, this is the address OE0459E8 that you also have written here. And we are loading this address into a register x1, and we are branching to that. We are jumping to that. And of course, how does the x1 and the notice work? The notice works by taking the first parameter in x0, and so in x0 you put a pointer to a string, basically. So this is exactly what we are doing, and in x0 here we are using the pointer to a string, which is basically directly after the payload. So this is our payload. If it runs, it's going to print ISRG. So, but where are we writing this? We're going to write this by using the mem copy, and this is the SMC ID. And how do we know that? We know that because the mem copy that we hear is triggered with the SMC ID is 180 4180. So we are going to call that SMC ID. This is our X1, which is the destination. What is this destination? Well, it's pretty easy. So we are actually overriding directly the SMC handler. So we use this mem copy in order to change this code. And this is possible because the MMU is disabled, as it was in the target at the time. Again, if you're thinking about doing this on a modern mobile phone, this is probably likely not to work. But if you're going to do that in another different device, or in an ECU that has not been, let's say, properly configured from a security point of view, then this is actually going to work beautifully. So we're going to override this SMC handler, and then we're going to call the SMC handler again in order to run and execute our code. Well, I already prepared the binary. Let me enable the share. This is the solution that we have. And indeed, this is actually what's being printed on the screen. But this printing has been done by TE code, by execution of TE code. So this means that and this is done by the execution of our own payload that we have done. So basically, with this just simple printing, it means that we have executed this shell code, and it means that we have been able to supply code from the RE that was overriding the SMC handler, and basically we have breached at least the separation between RE and TE, because we've been able to write in TE memory and to execute code supplied by the RE. So this was just a very brief example. Again, don't be surprised of the MMU. There are still devices where you can still find it. Okay, let me switch back to the presentation, to the slides. So our live demo has been done, actually demonstrated that by you being able to write in your TE memory, you're also able basically to execute a number of things. This is not always possible. This is still possible even if the MMU is enabled. There are a number of tricks. You have the return-oriented programming, but this was just making the point that if you have an ability to write anywhere, or if you have to be able to build the equivalent of a mem copy, then basically you are completely executing, breaking the TE. The whole point that we also want to discuss is how do you fix that? in general. The real point is, why do you even exist in the first place? And this is actually the great point made by the guys at Apertis at the time. The SMC interface is critical. There should be no way of being able to write or read TE memory. And this is why the SMC interface is nowadays very well guarded. It becomes quite difficult to find vulnerabilities in SMC interfaces in advanced TEs in mobile phones. But there are always exceptions, of course. The only fix possible for this vulnerability is actually to remove the MCPUI. There is no purpose for MCPUI in an SMC interface, because the whole point is actually making sure that you are not able to read out and write in TE memory, and then basically you are giving me back to the RE, to the attacker, the ability to do so. So in general, the lesson here is that you need to remove not only the MCPUI, but also all the primitives. So if there is any way that I can pass a pointer that is actually executed upon, even indirectly, then it's basically looking for trouble. So you need to be able to say, hey, I don't want this pointer because it points to my own memory, to the TE memory. So the TE must know what is the memory which is secure, which is used by the TE. So there must be a way to do so in order to be able to filter and distinguish. Well, the typical approach is that to implement some range checks. The software is used to determine if pointer or range is valid. Well, what does it mean valid here? That the pointer does not fall within TE memory, does not point to secure memory. And that the range does not overlap in any way with secure memory. This information is stored in tables, usually. So for example, in here you have the base and the limit. There is a range error. And this is just a very simple example of a number of things that can be used for taking a range check. And you will find them in any TEOS, in any software that needs to deal with input from the RE. In one form or another, they are there. And the basic the information is used is stored in tables. The point is that if you are able to modify the tables, then even with one single byte or one single bit, you may be able to bypass the range check completely. You don't change the code, you just change the data. And keep in mind that the data section, data pages are usually marked as writable. But if you change the data upon which the range checks to actually occur, then basically you may be able to bypass this check, and then enlarge your attack surface, passing pointers which you should not be supposed to do. So what are the caveats here? Is that these checks must be consistently applied to the entire interface, and this is not so trivial, because especially in structured communication, you have pointers which are hidden in several several structures or several layers of structures. So this may be not that easy in general. The tables must be correctly maintained. Why? Because secure ranges can be dynamic. What is the example here? Well, basically, when you are watching a video under DRM, the video frame buffer is under TE control, or at least for that part of the frame buffer. When you're going to use the screen for playing a game, usually that implies that the frame buffer is under RE control, so non-secure. And this switching happens anytime that you actually switch to a different application. So these tables must be maintained dynamically, and that can be also prone to mistakes. The table must be not compromised. If you're able to modify that from an attacker point of view, if you have a primitive, well, basically it's bypassing range checks. And this is exactly how Gal Beniamini used a vulnerability in 2015. And the vulnerability, which is visible here, I'm not sure if you're familiar with ARMv7 assembly, is actually down here. Let me have a very quick brief look how this is seen. So the parameters are, let's say, R0, R1, and R3, and so on. They are used, let's say, in sequence. So the first thing that we notice here is that R1 is stored, R0 is stored in R1. So this means that this function only takes one parameter, R0. R0 is the parameter and is stored in R6. And if you briefly go through this, through the code, you see that R0 is destroyed here. So the value is actually destroyed. So you arrive at this function that the only value where is your data, your point, is in R6. And this is untouched. If you actually look at it really nice, it's more easy to do, but R6 is not changed at all. So if you're able to reach these bridge here in some way, then you will get that 0 goes in R1, and this 0, the content of R1 is stored at the location of R6. And there is no check here. So this means that you can pass a physical pointer where you actually can write a 0, well, a 32-bit 0 in at that location. And basically, this is how Gal Beniamini used this null override anywhere, used for bypassing range checks. And if you're interested in this, we would advise to have a look at very interesting attack. So there is much more, but it's just to show you that pointers are the really Achilles heel of, or historically been the Achilles heel of TEs. And we do expect that this is still going to remain the case, especially for devices and TEs which are not as mature as other industry like mobile, payment, pay TV, and where the TE has been, let's say, very likely scrutinized by researchers and by companies. So, okay, Cristofaro, you are referring to vulnerability from 2014 and 2015. Yeah, they still have a point. I mean, because we think that some devices may still be at that level of security. And yeah, we think, but we also like to prove stuff. We also like to have the possibility to show that what we are saying actually really applies. So this is our research from 2020 and 21. Well, it's been submitted in 2020 and 2021 has been published. So we had a look to a Qualcomm IPQ 40XX SoC. It's widely used in networking devices. So basically, if you have a router at home, chances are that this chip is in there now. It supports secure boot and supports Trustzone, and includes the Qualcomm TOS named QSE. It's fair to say that the QC that is being used on this device may be different from the QSE used from on the mobile platform. We don't know that, but we know that the name is the same. It's still QSE. Still, it doesn't mean that the vulnerability that we may have identified are necessarily portable to other SoC or mobile, to a Snapdragon SoC, for sure. They're surely applicable for this SoC, for this system on chip. We found indeed 4 vulnerabilities, and we initiated a coordinated disclosure with Qualcomm because we immediately understood that this could have been very serious. Having devices all around the world that would allow, say, code execution in a way, or vulnerabilities in the highest level of privilege available in the SoC, in the chip, then it's always something to probably remember and have a look at. So we've been assigned with 4 CVs, and it's memory corruption due to lack of check and validation of pointer. So this is exactly what we have been describing and what have been using in the research from 2014 and 15. So this means that this is still a thing, especially in some devices and classes of devices. That's why we are saying, and we do expect that this vulnerability we're discussing now, although they might seem old and dated, they are still applicable in terms of effects, or in terms of class of vulnerabilities. And this is the Qualcomm Security Bulletin in January 2021. And what can be achieved? Well, you can achieve code execution DIS privilege. The TE can be fully compromised. Any TA secret can be retrieved, and then you have unimpeded access to the hardware. The requirement is just to send the SMC calls to the TE, exactly as like we have seen before. So if you are able to send the right sequence of SMC calls to the TE, you will be able to leverage the vulnerabilities in order to execute code. Well, we have a video because that's exactly what we did. And let's have a look at this video now. So we demonstrate arbitrary code execution with one of the CV that we have found, that we have been assigned. So what are you going to see now in the screen? You are seeing the serial interface of a device. And you see that a device with the IP QSOC. You see that the QSC key execution is started, and after there is U-boot executed. So this is the execution of privileged code of the untrusted firmware and the initialization of the TE. And in here, you're already executing the bootloader from the RE side. So when you start seeing this screen, you are running code as DRE. So nothing really surprising here. We are going to stop during the boot. Why? Because in order to prove our point, we just need to send SMCs, and you need privileged RE code to do that. So you need to be either the kernel or the root attacker who is able to load a kernel module, or user space non-privileged attacker, just a normal user that use some functionalities in order which may be present on the device. In order to send SMCs. But this will be always device dependent and model dependent. We wanted to have something that demonstrated the point beyond the differences between devices. So we actually, what did we do? We implemented some code in the bootloader. Without going into too much details, we don't have the time now, but for sure there will be in the future. Code in the bootloader that sends SMCs to the TE. Exactly how a privileged attacker would be able to do. So let's continue and see what's going on. We are fetching our exploit, and let it finish running. A few seconds, Niels, and then we are going to briefly comment it. Great. Okay. So we have used the vulnerability to disable TE secure ranges. This is exactly what Gal did in 2015, and this is exactly what can be possible. And from an attacker methodology point of view, you want to enlarge your attack surface. So if you are able to, let's say, write somewhere, basically, the first thing that you could think of is disabling the secure ranges in order to expand the ability to supply to TE pointers. So then we used these the additional attack surface that we gained in order to create our read and write primitive. So we built our own memcpy. Of course, it was not there, but by binding and different calls and number of things, we have built our own primitive, which also now boils down to what we proved already in the first demo. If you have a memcpy in your SMC, then basically the game is almost over. So what did we do? We didn't copy our payloads in the TE side. We just instantiated our own payload on the RE side, so it's non-secure memory. And we used inside our memcopy in order to patch the MMU tables and say, hey, this memory where it is our shell code is executable. We just patched that briefly, very quickly. And after that, we took control of the program counter and we execute its own payload. So what does the payload do? It just dumps the register that Niek was referring to before, the SCR, the secure configuration register. And the bit 0 of that register is DNS bit. Now, DNS bit here has been dumped is 0. So this means that when the register has been dumped, the bit was 0. So this means that the code was being executed as TE. So this means that this dump of this register has not been done by RE code, but by TE code, which is exactly the payload of our attack. In general, so we were able to demonstrate arbitrary TE code execution, and by using a vulnerability. We use the vulnerability basically to disable the secure ranges. There will be more information on this part. Again, we simply don't have the time because we would like to give you some more insight. So let's go back to our presentation. Which is here. Okay. Great. So we demonstrated how this is possible already on a normal device. What we didn't know is that not only the SOC that we investigated was all impacted, there were impacts on other SoC, on other chip, and some that we did not expect as well, Bluetooth and also power line transceivers. We recommend to refer to the Qualcomm bulletin for the full list. It's fundamental that you follow that advice and that you check that, let's say, if your device has could be prone or could have a QSE. And why this is not trivial, or that can be trivial, because even if your device, your product is not using the TE, chances are that the TE is still there anyway. For example, we didn't find any use case for the device that we were investigating, but still the TE was there and available, because it's not something that it's not a feature that you say, hey, I don't need it, buy. Well, you could do that, but not, let's say, easily yourself for a device in field. So we have seen that how, let's say, a simple control of a byte or of a bit would allow you to take control on the T side. We didn't do anything, let's say, fancy. We just patched MMU tables and so on. We could have done much more interesting exploitation, but for this time it was a right point to prove this. Now it's also possible to attack TAs, and one of the interesting paths is through shared memory. So why do we need shared memory? Because the interface to SMC is too narrow for bulk data processing. You can pass up to 7, I think, up to 7 different values, but that's it. But you can pass pointers, and you can pass a pointer to shared memory. The point is that shared memory must be RE memory, and therefore must be allocated by the RE. And the reason is that if it is TE memory, it cannot be accessed by the RE at all. So that must be RE memory. It's typically used for communication between the client application, so the RE user space, and the trusted application, the TE user space. And it's in many cases it's always accessible for the RE. In other cases, it only has it has a lifetime, which might be the duration of the call to the TA. Another thing which is interesting is our global platform API, which is a standardized interface provided by a global platform. To our knowledge, it's implemented in most of all, maybe, trust zone-based TEs. So even if a TE has its own native API, chances are that this global platform API are also there. And they are present in both worlds, in RE and TE, because you need to have them on both sides in order to properly marshalling data between the two worlds. So you will have libraries on the TE side to be integrated in the trusted application, and on the RE side to be integrated in the client application. So one interesting path here is a type confusion attack. In general, this API support communication. The communication use shared memory, and the communication also requires user typed attributes. So the command sent from the CA to the TA can rely on multiple parameters, up to 4. But the parameter type must be declared. So you need to specify from the RE if it's going to be a value or if it's going to be a mem reference, a pointer to memory. Because in general, the RE is allocated in the shared memory and using typically the mem ref for saying, hey, the shared memory is at this address. Because in Global Platform API, any CA memory buffer can be declared as shared memory. So you don't know in advance. In general, for the GP API, the shared memories are located at runtime, or it's declared as such at runtime. The REOS will transfer the reference, the user space reference, into a physical address, or the hypervisor if there is any, and the TOS will map the physical memory into the TA address space and translate the reference to a TA virtual address. You need to have this approach coming from both sides in order to make the shared memory visible to the trusted application. Now, of course, we have seen that pointers are a bit of an issue with these, always. So you need to check that the pointers that the RE is passing actually are pointing to RE memory, so not to TE memory. So this means that for memory type, there is a check which is done in this function for opt-t. It's just an example, but there is equivalent check in other T's, in other TOSs. So there is a check that says, hey, if the pointer you're passing is pointing to secure memory, I don't want it. It's not good. You see that for values taken from the RE. So what is passed from as a value is just read. There is no check. But if we pass a pointer, then the TOS must check. So what is the type confusion? The TOS can perform checks only if the passed type is a pointer. You cannot check a value to be matching secure memory. No, it does not make so much sense. But if you're passing a pointer intended to be used as a pointer, then it can be checked against ranges and so on. So there will be, again, the range checks that we discussed earlier. The point is that the TA must check the type for the incoming parameters, because the TA should also be able, hey, you're giving me a value, I don't want it, you should pass me a pointer. Because if you pass me a pointer, then it's going to be checked by the OS. But if you pass me a value, it's not good. But if the TA does not perform the type check, it may start using a value as a pointer. Because I could declare that numbers that the TA is going to use as a pointer, and I can just say to the OS, hey, don't worry, it's value. Don't use it. There is no check to be done. So this pointer would point to memory owned by the TE. This is also true for values, or if it's an offset to a pointer, that can be still problematic. So we have done a few other research, basically. We are still, let's say, in the process of discussion. So let's make a very, just a basic example of things that, how things can go wrong. So you see that basically here, outbuff is taken from the buffer pointer passed from the RE, which is the third parameter, which is used as a memref, and there is a buffer. So this is a pointer passed from RE. The function does not perform any check. The TA does not perform any check, basically. It just uses that as a buffer and as a pointer. And then it copies to this destination the value that we are passing for the amount that we are passing. So this is also under control. So basically, we have an arbitrary right in the TA address space. So we need to pass a pointer value that makes sense in the TA virtual address space. So the outbuff can point to any TA memory. And so you have an arbitrary write of TA memory. So this is also still quite common and to be found. Let's have again a live demo, but a bit shorter than before. Let me switch to our so we just start another module here. We exit and we start module number 9, which is typo. We just run it. Again, this is a different device from the other one. So this is the different instance of the device. So the vulnerability that you have seen there is not there anymore. So there is a TA here, which is called typo, which is performing a number of checks and communication. So what we're going to see, what you already see here, is that TA invoke command entry point. This is what is called, and there are also a number of maybe I should make it a bit bigger. Yeah. Let me restart it. Yeah, not everything goes always. Yeah, okay, maybe we should see a bit better now. Okay. So there is a TA which it seems it does not check the pointers and the values that we actually pass. And we also have another project which already yeah. So we should have a function here, TA invoke command entry point. And this is the function that processes our commands. So there are different printout here. So we have a TA set version by value. And so what's happening is that the value that we passed is directly written into the global version. That's yeah. So we also set version by reference. It's possible, and the value is taken as a pointer from what we actually pass. So we pass this as an address, and there is no check here if it's a value. It's an address. We just used any point in time. So we also can get version by reference, and we also get version by value. So we can either pass a value, so let's say give me the value of the version, or we pass an address, like store the value, the version at this address. So you have a number of primitives that are interesting to be used, because in principle you can pass anything here, and you can actually write the version, but you can also set the version. So in principle, if you set your version by value and then you get version by reference, you set the version by value to what you want, and then you get version by reference to write where you want. And this is exactly what we are going to do in our exploit code. And we are going to have an arbitrary read and an arbitrary write. So if we write to a specific location, we'll get a flag. And if we read out from a specific location and compute and do some computation, have some value, we get a flag. Otherwise, and also if we are able to write to a specific location, in that case, we also get a flag. So it basically boils down to that. I have already done So for us, it will be just be able to see the flags. Don't worry. I mean, in our trainings, we change those flags, so this cannot be used. And so you see that we are going to do this, and indeed, for the second one, what we did is we are going get version by reference, and sorry, we're going to set version by value. So we set that to the value that we want, and we use the get version by reference to write to this address, which is a valid address within the TA address space. Of course, if ASLR is enabled, you need to have a way of getting the memory map of the TA. So you might need an information leak. You might need to have other capabilities. But basically, this is it. So this is how you actually exploit type confusion. Well, you pass, you declare a pointer as a value, so that it is not checked. And on the other side, from the OS, and on the other side is still used as a pointer. And at that point, basically, you can get arbitrary read and write to in the TA memory. Okay. So let's go back to the presentation. We should be able to see that now. So what was missing in our function? This was missing. On the TA side, there is just a simple check that must be done. That if your parameters you're receiving are not matching what you want, then you don't accept. So even if I pass something as a value on this side, it will not be accepted because it should be labeled as a memory reference. Because if it's labeled as such, for sure US has performed the range checks. Now, also cross-TA attacks are possible. We are going to have a look at this specific scenario. So we assume that we are now in control of a TA, and we are having a look to a bit of exotic attack, just to show a bit of our points that we've been trying to make. For a TA, the access to hardware is needed in general, not necessarily directly. It's usually mediated by the OS as usual. But the hardware IPs may perform operation with TA-specific secrets, like cryptographic accelerator. Think, for example, a payment application that needs to decrypt keys, or your, let's say, data which is encrypted with specific authentication key framework authentication framework of Android. The access in general mediated and can be restricted by the TOS. But sharing the hardware modules or sharing the use may lead to cross-TA attacks. And let's have a look at this example, which is the Ledger Nano TE. This is something which really happened. The Bolos OS is basically the TOS, and the hardware is supporting as a secure element, supporting untrusted primitives. So what is the point of what was the issue here? Finally, says the OS provides memory isolation. Good. It means, for instance, that the Bitcoin app cannot access the data of the Ethereum app. So, I mean, it's expected that one process cannot read the memory out of from another process. And this mechanism is enforced using the MPU or the MMU in more advanced, in bigger SoCs. But what was forgotten here, or really, or maybe not considered, we don't know actually. When an app is installed, it can derive any key path. So this means that when you install an app, you can derive the keys for any other app. So even if the memory isolation is implemented, so you cannot read the key from the memory, you can still ask the hardware, hey, please, can you give me the key, the private keys for this other app? Because this means that the access to the hardware, the separation was not there. In fact, this is what some people sometimes is dismissed. Of course, I mean, it's historically known that memory access or memory access to other memory separation must be there. It's there even for another EOS. But what is often neglected is that the IP separation for a TE must be also there. So basically, there should be a way for the OS to say, hey, your identity is not matching the resources that you're asking from the crypto. The MPU has no role here. The TOS should be, in our view, responsible for doing this kind of association between the identity and so on. So that's why the IP separation is something that you need really to take care of and is usually not considered when thinking about an OS. The assets from TA, the TA needs adequate protection because the assets themselves need to be protected from other TAs. The TAs will always rely on hardware for some operation. So this means that having MMU is not sufficient for separating TAs in a proper way. While this may be sufficient in other situations where the access to the hardware is not critical, when secrets cannot leak, in a TE, yes, it's relevant. And this is one of the biggest difference in terms of design for a TE or proper TE. We need system level thinking for approaching this. Because the TOS is not just another kernel, it's some specifics to that, because there are additional properties that needs to be considered. Hardware IP is not IPS, I'm sorry, IO subsystem. Memory and execution separation are not sufficient here. So there are other attack surface that we are not considering in this talk, just simply because we don't have the time. This is, of course, the TOS. You may be able to attack the OS directly and not the TA or the monitor. But it's rarely reachable directly from DRE. It rarely has a direct interface that you can talk to it. It's usually done through the monitor in some way. And the trend is always to restrict the amount of services that are available to in the TOS. Nonetheless, the attack surface, the interface between the TA and the OS, which implies having an SVC, supervisor call, is very rich. It's basically the syscall interface for the TA. The OS also does not typically contain secrets. The platform secrets are usually in hardware or some form of, and the use case secrets are usually in the TA. The OS has only the power of performing operation and giving you unfettered access to the entire system, but it does not have its secrets in itself. But if you compromise that, you have access direct to the hardware and to other TAs. So basically, the TA to TA separation is gone. Another thing which is relevant to be considered as an attack surface is that secure boot initialization. Secure boot is the cornerstone for TE security, and bootloader vulnerabilities may compromise the TE. And this is, for example, things that we actually have a close look in bootpawn. And incorrect configuration may leave room for attacks. Just think for a moment if the switching from RE to TE, some memory which should be secured, it's not secured. Just because the tables or the MMU tables or range checks table, the controllers, they are not properly configured. So if all this configuration do not properly match, then there may be room for attacks. So what can be done? What are the considerations that we can do? Industry adoption. The mobile industry has by far the most mature TE ecosystem that we are aware of. So there are security reports, bug bounty, security contact, there is proper triage. So there is a proper, let's say, security approach for reporting and fixing and mitigating and reacting to vulnerabilities. And we're talking about TEs only, of course. I mean, there are other industries which are as mature as that, as the mobile ones. But for TEs, we can say that they are by far the most mature. Other industries and devices are catching up. They are at a different point. But for many vendors, they are still missing even security contact information. So even if you find something, you're not even able to reach that. And also because those devices are really scrutinized by researchers. We do expect that serious vulnerability may surface for such devices just because they need to still mature to reach to the same level of the mobile industry. So what can we do for preventing a number of things? Well, first you need to have a threat model. It's fundamental. You need to be sure to understand how an attacker could attack yourself, what is relevant for you, for your product. And you need to keep a system level view. You need a clear understanding of security boundaries and interfaces. This is critical because otherwise you may miss a lot. And this is also what, for example, what we have just seen for the Ledger Nano discussion. This is what we think. We should not consider hardware and software as separate entities. There are interesting discussions on Twitter also on this, and it's especially true for TEs. They concur in creating your environment. If you don't have a look at software, then hardware alone will give you a brick. If you don't look at hardware, then software will just be as vulnerable as any other software. So the environment exists because they work together. So every time that different teams look at different things and say that this is good and this is good, you may end up with a flawed product when you actually put two goods together. So you end up in a situation where good plus good means vulnerable, just because you have not considered them together. So you may want to perform regular security reviews, and testing is part of the basic hygiene. And if you have suggestion what to test, when to test, or if to test, just feel free to reach us, of course. Response. Be prepared. Don't postpone, let's say, the ability to respond, because vulnerability will be found and it may be too late. You just end up in a mess. There are, by the way, a very nice company that may help you in building this process of vulnerabilities, of triaging, let's say there are for sure companies which are mature in supporting you in establishing that. Because handling the security and incident handling process is vital for making sure that you are able to improve, and so that one vulnerability does not bring to a catastrophe, basically, or to something very problematic. You need to have security contact points, vulnerability analysis, you need to create and test patches, you need to have communication. Collaborate with the security researchers. One of the most, let's say, problematic way of securing a product in history has been when a defensive approach towards researcher was taken, or even if not hostile. We had to learn our own way in the IT industry, and also in the mobile industry, for example, now that shooting at the messenger is not the right way. You will probably just not be messaged again with another vulnerability, and you will be vulnerable forever. So this is our suggestion: collaborate with researchers. Mitigate. Make sure a product can be updated. We know how difficult this can be in the automotive industry. We know that technology and the ecosystem still needs to make take some effort in order to make sure that you are in the position to securely and safely update a component. So that's why there is so much discussing about OTA. You need to reduce privileges and attack surface. Less is always better in this case. And please do evaluate the exploit mitigation. They are there, they've been invented. Don't dismiss them as, let's say, we will think about it later. And this is, we think that's the right way to approach, because, for example, Microsoft had decided a long time ago that there was no way of fixing 1 millionth vulnerability of their products. But there is one way of making 1 million of exploitations difficult. So that's why the research also moved to exploit mitigation. Well, we would advise that if you want to improve, you need to learn from attackers. Keep yourself updated, analyze attacks. If you need some help, just reach out. There's no problem for that. That's also why our training are looking from an offensive perspective, because you need to know how that works in order to properly protect yourself. And if you want to avoid pitfalls, talk to people that have already implemented or reviewed or worked with TEs already. It's very easy to forget something when in the design or the implementation. Develop your internal knowledge. As far as we know, TPON is the only training available on TE security. We are very glad we've been at the forefront for this, but we also think that training is not the only way. You can also do a number of different activities for developing internal knowledge. So a conclusion. In this talk, It's been a webinar, quite long. We hope it's been interesting. It's now 1 hour and a half. We explored the T attack surface. We have shown real attacks. We have analyzed. We have seen how things which you would dismiss, yeah, this is not actual anymore. This is not true anymore. They still apply in many different situations. We have discussed, we have seen live demos of a few attacks. We used our own platform for doing that. And we have done, you've seen also a video of an exploit and very recent, and we discussed the mitigation. And finally, we discussed a few recommendations for T-security. If you want to know more, that's all from our side. But if you want to know more, reach out, and our blog will constantly provide, let's say, information, and you will sure find more on our research over there. And if you really are interested in these topics, there are a few upcoming trainings on secure boot and trusted execution environment. And I think it's time for questions, or maybe if Niek wants to add anything, but if there is a possibility to take questions at this moment, we are both available.
So first of all, Cristofaro, thank you so much. Niek, thank you very much. What a great presentation. Not only theoretical, but showing the application as well, and then potential recommendations. I especially like the conclusions as well. I think it's really important, and I think you demonstrated it very well here. You know, we in the automotive industry, we try to do things ourselves a lot of the times, right? And sometimes we can only get to a certain point of hardening, or only get to a certain point of keeping track of all these different things. And it's sometimes really necessary to bring in the experts like yourselves to really take a look and make sure that the TEs are properly configured, or that you know, these types of things that are potentially you know, threats to our businesses, that they're hardened. They're not in the software, because as you demonstrated, well, a TE is also just a way. It's just 1-bit separation, right? So first of all, we have a lot of questions. I would just ask a few questions if you guys don't mind taking a little bit more time with us.
Not an issue at all. We are here.
So the first question is coming from Esteban. He's asking, does TEE mean that you may need some libraries twice, once for REE and once for TEE, just to ensure that the TEE has a separated environment?
Niek, let's take one at a time, unless we have a specific preference. Okay, would you want to start with this?
Sure. Yeah, so the idea is that the software from the RE and the T is completely separated. So if there's any functionality, for example, libc, that's implemented on the RE side and on the T side, so it's used, then that means you indeed have to have that library on both sides. Because the code that's running in the RE and in the T is really separated, so they cannot reuse each other's code, because that would violate one of the separations that needs to be in place when you want to implement the security.
Niek?
You did not hear me?
I think you dropped out quickly.
Did you hear anything I said?
Yes, sir.
Up to the point of the fact that libraries will be probably maybe duplicated or replicated between the two sides.
But that's where I ended my answer, I think.
Oh,
okay. I put the reference model for a better discussion on the slides. So
what you see, let's say the RE side, you see no blocks there now. It's completely black. But in reality, there's things there, right? So there's maybe a Linux OS, there's applications there. There's definitely libraries, for example, a libc library. So these will be available on both sides, because typically you also compile the trust application with libc. But the libraries that are specific for the TE functionality, they will not be present in the RE.
All right, so there is real separation here, and we would have to have potentially two sets of libraries that are providing the same functionality, just in two different operating environments.
Yeah, so that's also one of the reasons why it's referred to as the rich execution environment. There's much more code typically available in the RE. So if there's any overlap between the RE and the TE code, it is likely very minimal.
Okay, great. Thank you. The next question that we had, I think it's more just confirming the discussion here. It's coming from Scott. The TEE single register bit that controls secure versus non-secure operations. This can only be controlled by the REE kernel and limits access with the different trust levels on the processor. Ring 012. Is that correct?
Let's try to answer this with a different slide. So this bit only exists and is accessible only to the monitor. So this bit is a secure configuration register specific to EL3. So this bit is not even visible from the RE side. You cannot even check it, basically. Well, in principle, that can be reported by the TE or something, but this is accessible only to this monitor. So it needs to be more in the monitor mode in order to actually check this bit and change it. So no, the RE cannot change this bit at all. What happens is that the RE is going to ask a service, so do an SMC, and the monitor on the other side will trap, say, okay, let me service you, and let me see, let me change this bit from 1 to 0, because this is not secure. And when it's changed to 0, then basically that's where you are in TE mode, also for the rest of the system and not only for the monitor. So the RE has no availability of this bit, not even in access. The entire RE, regardless of the exception level. Because the RE has exception level 2 and exception level 1, and none of them, and 0 of course, and none of them can access this register. I hope this answers.
Yeah, actually, I would think that there's a lot of attack scenarios which are focused on controlling this bit. Do you see this?
No, not in software attacks, because this flipping of this bit is actually done as soon as you enter in the TE, regardless of if you want it or not. So when you are running TE code, this will always be flipped in general. So the point is not so much in flipping that bit from the RE, because you don't even have access to that. So from software is not possible. Different topic is instead if you're applying fault injection attacks for hardware attacks, because you're not trying to change the bit by accessing with software. You're trying to do that with a glitch. So I think there has been a research some time ago of flipping, 2017, I think, flipping a bit with laser, for example. But that makes sense only from a hardware point of view, because from a software, there is no way to do it unless there is a hardware level flows, which nobody's aware of at this moment.
Okay. Very good. Great. Thank you for the answer. Then another question from Esteban. What memory protection unit separates the TEE and the REE memory? Then the REE should not reach the TEE part, or is he seeing this incorrectly?
No, I think his remark is correct. So a memory protection unit is indeed what is used to enforce restrictions within memory. So typically what you can do is you can define regions inside the memory itself. And then once accesses are being made to those regions, the MPU is able to allow the transaction or not. So for example, if the RE would access a region that's defined as a secure region, the MPU simply will drop the transaction. And for reads, that typically means that you get zeros back. And for writes, that typically means that they're simply ignored. And depending on the granularity that the MPU allows, you can have just a few regions or a lot. That really depends on the MPU's design.
Great.
Oh.
Thanks, Niek. Next question coming from Scott again. Does the TEE generally have ASLR turned on, or is that even possible?
Good question. Okay, it is possible, first. Second, there are TE OSs that we are aware of that uses ASLR at least for the TA, but also for the TOS in some cases. It is possible, but the functionality is very limited. Can be limited, actually. The amount of bits of entropy, this is one of the limitations, is very small. And the reason is that even if you actually move the TOS, you cannot move that a lot, because you cannot move it in the entire memory space. You need to move it within the secure memory, which has been configured in the controllers. So if the controller says, hey, between here and here, you are a secure memory, and this is what I'm going to protect, you can move the OS in principle, but you need to stay within that range. So that's why, yes, ASLR is possible. Yes, it's also implemented in, let's say, mobile phones, for example. And but the amount of entropy that you get is not as large as you would get on the RE side.
Okay, great. To try and reduce some of the questions here, we have a lot of questions. So, guys, I don't think we're going to get to all of them today. I'm sure that Cristofaro and Niek would be happy to answer them also by email as well. But let's ask one more question here. So Alfie is asking about the bootloader as a second component in the chain of trust and the closest to the root of trust here in the ARM CPU. Must be really secure, otherwise it can compromise the TEE, as you also mentioned. My question is there a way to authenticate bootloader using TEE and an external chip to the SoC provisioning keys and certs? Just to add, this chip also supports crypto auth operations like a TPM. Who would like to take that question?
Yeah, that's no problem. So basically what typically is done, and also what is the one of the best approaches, is to make sure that you implement a chain of trust that's embedded in the hardware. So this typically means that there needs to be some form of cryptographic primitive, for example, a public key that is embedded within the hardware and it cannot change, because if you can change this, you can affect the chain of trust. So once you have this and you couple this with some code that cannot change, and all chips have this is the ROM code, then that allows you to make something that's called a root of trust. So that is what we are also depicting in this picture on the bottom. So once you have this piece of code that can use this key, it's able to authenticate the first stage bootloader. Now, once this first stage bootloader is authenticated, then this bootloader, which is authentic code because we just verified that, is able to authenticate the next one, until the entire system is initialized. And if you do this properly, you do not need any external components. And also you do not need the TOS to authenticate any of the bootloaders, because they will be already long gone by the time the TOS is executed, because the bootloaders execute way before that. Now, the more complex the device gets, the more complex the boot flow gets. So it's not always true that all the bootloaders start before the TOS. But what you often see is, for example, that you have different boot paths where different components like a TOS and an REOS have their own bootloaders. But as long as you have a chain of trust that is embedded in the hardware, which you typically see for many of the modern chips that are available in the market now, because they market this type of functionality as secure boot. You do not need any external chip for offloading, because the key material that you rely upon is basically not something you need to keep a secret, because you only have to store the public component of the authentication within the chip. And the private component you can securely store somewhere at your own premises, far away from the device that may be under attack.
All right.
May I add something, because that might be a bit so interesting. Keep in mind that at this point in time, secure boot is actually supported by untrusted firmware. So it's already out of the box. This means that if you're using an SoC-based product and it supports secure boot, chances are that you can just use untrusted firmware in order to make sure that all of your bootloaders are authenticated. This is also what we are doing in our platform. You see that's here, secure boot is on. And we actually, what you're seeing is untrusted firmware authenticating the next bootloaders on an ARMv8 platform. So the platform that we have has secure boot already. And indeed, this is already authenticating all the bootloader, BL2, BL31, all these things. So this is actually possible already, and you don't need necessarily to resort to custom design, which is, of course, prone to mistakes in general. So my advice is that if the SoC supports secure boot and untrusted firmware supports the SoC, carefully evaluate the reason why you should not use it. So you should have very good reason not to use it in general. So I think this is just for completing a bit of the answer and giving some suggestion insight. As you can see, it is not pure magic. It's something that we can even do even without being an SoC vendor or a device vendor.
Great. Thank you, Cristofaro. Okay, that's all the time we have for tonight, guys. Before we close tonight, Cristofaro or Niek, would you guys like to say something before we close?
Yeah, please.
Go ahead.
We would like to thank you, first of all, for us being here. And we think that these events actually allow to make different expertises to meet, even if in a COVID world where meeting is difficult. So we would really like to thank you for this initiative. And for sure, we would love to also to contribute more on this topic in general, because that's also our part. By the way, should anybody would like to have a presentation or a final presentation at their own premises, company, or something like that, we are certainly up for that. So don't feel afraid to ask, hey, can you give this presentation at for this company or at my company, or and so on. We will really be happy, because we think that the more we understand now, the less pain we will endure after.
Niek?
No, I have nothing to add. I would also like to thank you. It was a very positive experience. Thanks.
Great, guys. Well, I need to thank you guys because it was a great presentation tonight. I think it's really interesting information. And the more we know about this, the more that we know about TEEs in general, how and what not to do, makes hopefully for better products in the future. So really appreciate you guys doing this tonight. And for all those that are still listening, please come back next week. We have another really interesting talk. Actually, I think 2 talks next week. So come check us back, asrg.io, where you can find all the information about what's coming up in the next few weeks. All right, guys, have a good evening. We will talk to you or see you next week.